Hi, and we are on our last lesson for this unit. So let's take a look at what is called a decay model. So we're mostly going to be focusing on half-life, but this model works for any value that decays. So for example, when you take medicine and it decays in your bloodstream, we could use this to model the amount that's left after time. So if we take a look at the equation, we have y equals a times e to the negative b times t power. So y is the amount after time, what's left after it's been decaying. A is the initial amount of the medicine or the material that we're looking at. B is what's called the decay constant. That is different for every material that is decaying. So we'll have to find that decay constant every time we have a new question. And then T, of course, as always, is time. By the way, this sheet for your vocab was not on the original vocab sheet. For some reason, I missed that when I was getting the vocab sheet ready the first time around. So I did update that and repost the vocab sheet to the website. So if you have not yet started to fill in your vocab sheet, you can just grab the new one. If you have, grab the new one and just slide this page at the end of your vocab sheet. All right, so starting off with our first half-life question. So a lot of radioactive substances decay at what's called a half-life. So we know how long it takes for half the material to decay. And what you need to remember is that if you start with 1 gram, it takes just as long for that to decay to half a gram as it does for 1,000 grams to decay to 500 grams. Remember, this is an exponential function decaying at a half rate. It is not talking about the quantity that decays at any given time. We're talking about the ratio to the amount that we started with. That's the half-life. So, first of all, we are asked for the decay constant. So let's jot down our formula. Y equals A times e to the negative b t power. Again, b is that decay constant. That's what we're solving for. So we should be able to substitute in for everything else, remembering that e is a number, so we don't need to substitute for that. A is the initial amount. We're actually not given the initial amount, but we do know the half-life. So think about yesterday when we saw those interest rates doubling. We may not have known the initial amount, but the first step is to divide by the initial amount. So if you think about, again, if it helps you to set it up, to think about that initial amount being 1, and a half-life would be it decays to half of the amount that you started with. Again, that decay constant, or b value, is what we're solving for, and t is the time, how long it takes for half of the material to decay, and in this case, our half-life is 3,685 years. So we substitute that in, and then to solve for b, we of course are first going to divide by 1, which doesn't do anything. So to cancel the e, I'm going to take the natural log of both sides. So I'm left with negative, and I'm going to rewrite this as a coefficient, times b. So to solve for b, we're going to divide by negative 3,685. When you punch that in your calculator, you shouldn't need any parentheses. I would recommend using 0.5 for 1/2, so you don't have to worry about that fraction. And I got 0.000188. If you notice, you're actually given 1.88 times, and you'll see at the end the little e with the -4. So make sure you remember that's in scientific notation and convert it back to a real number. So there's our decay constant. We still don't know the initial amount, so we can't quite yet write the model. So that's our next question, is to find the initial amount. So we're given that information that there are 3 grams left after 10,000 years. So we're going to substitute that in. We don't know the initial amount, times e to the negative b. Now we know our decay constant, so we're going to substitute that in. And it took 10,000 years for it to decay to 3 grams. So to solve for a, we're going to divide by e to the nasty power. First, you may want to simplify that ugly power. Remember, when you multiply by powers of 10, hopefully you know this, you just move the decimal to the right. So we have 4 zeros on 10,000, so we're going to move our decimal point 4 places to the right. And it's a little bit easier to divide by e to the negative 1.88 to get our initial amount. And I got our initial amount is approximately, rounding to 3 decimal places, 19.661 grams, because we always label our answer. And finally, we're asked to use that information. We need both the decay constant and the initial amount to write our equation. So we substitute those back in. Y equals A, or 19.661, times e to the negative b, that's our decay constant, times t. Now I highly recommend with our b, normally we round to 3 decimal places. Because our b values tend to be very small, round to 3 significant figures. So if you have a bunch of zeros at the beginning of your number, keep 3 additional numbers. Otherwise you're going to get some serious rounding error. One more example. This time we're not given any hints about setting up our equation, but again, we need to know what the decay constant is for this new element. So we first have to start by setting up our equation to solve for that decay constant. So e to the negative b times t power. So we're going to substitute in the values that we know. We know the half-life, so again, half of what we started with will be left. So you can either drop that a or substitute 1 if you need that placeholder for your a. We're solving for b, and we know that it took 2,500 years for half of the material to decay. So again, canceling that base e, we're going to take the natural log of both sides, rewriting that 2,500 as a coefficient of b, and then dividing both sides by negative 2,500. We get a b value, or a decay constant, of approximately 0.000277. Now we need to answer the question. We're actually not asked for a model on this one. We're asked for how long ago was this artifact made, if there's currently 35% of whatever we started with left. So again, think about, we may not know the initial amount and we may not know the exact amount that we have now, but we know the percentage, and that's what this formula helps us with. So once we divide by the initial amount, so you can think about, if it helps you, you can think about if you start with 100 grams, 35% would be 35. The first step in solving would be to divide by 100, and you get 0.35. So essentially you can take that percentage and set that equal to the y value and just drop your initial amount. Substituting our b value in for that decay constant, and the question is, how long ago was it made? So solving for t, we need to take the natural log of both sides. Notice how this is different than solving for the initial amount. When you're solving for the initial amount, you have the value for your exponent. If the variable is in the exponent, that is when you need to use logs to get the variable out of the exponent. And dividing by the coefficient of our t, that decay constant, we get that it took approximately, the artifact was made about 3,970 years ago for it to have decayed to 35% of the original amount. And that is your lesson, so the last piece is your U-try problem. See you tomorrow.